When you prepared hydrogen in year 9, you did so by means of this chemical reaction, which I can write over here. You used zinc solid and you reacted that with hydrochloric acid, okay, to give zinc chloride aqueous, okay, and hydrogen gas. Okay, now I will put in the state symbol for zinc as solid, just to remind you that that is the reactant that we're most interested in right now. The zinc that you used in class was the granular zinc, okay? It's granules, okay? It's the silvery gray granules that you could cut up with the scissors or even pull apart using your fingers, okay? It's been designed for ease of use in the lab. Also, it's very easy to weigh them out safely. Zinc granules are easy to handle, they are safe to handle, there is no risk of inhalation, none at all. Also, the granules offer a large enough surface area, okay, where the acid can attack the zinc and react. And if there is enough area where the zinc can be attacked by the acid, then of course you are guaranteed of a good flow of hydrogen, a good safe flow of hydrogen that you could either collect in a test tube and test for using a lit wooden splint, or that your teacher could even collect in an inverted gas jar full of water, displacement of water, collection of the gas over water. However, the rate of reaction could be much increased if you had to take a single zinc granule and start to cut it up into smaller pieces using a scissors. Well, what you're doing is that by cutting it up, you are actually increasing the surface area because you are exposing more and more of the metal to acid attack. In extremis, if you had to use powdered zinc, then all of the zinc is ready for chemical attack instantly. Let's picture it in this way. Imagine we've got a zinc granule, and the zinc granule is a big lump. In order for the acid, okay, for the HCl to get to the zinc at the core of the lump or inside the lump, it first needs to remove the zinc which is found on the outside. So it first needs to react with the zinc that you have on the periphery, and eventually it starts eating its way into the lump. But since it's a lump, since it's a granule, the reaction takes place gradually. As more and more of the zinc is eaten away, it presents more and more of the zinc for reaction with the acid. But if the granule has been pounded or crushed into many, many fine zinc particles, then all of the zinc is available for reaction with the acid all at once. So the reaction, instead of taking 5 minutes to take place and for all of the zinc to be consumed, all the zinc can be consumed as soon as the acid is brought into contact with the metal, meaning that the rate of reaction will be initially much faster when there is a high surface area of reactant than when there is a lower surface area of reactant. Notice, we use the same idea as before, the same curves as before, but this time we are talking about subdivision or surface area of reactants. When there is a high subdivision or a high surface area of one or more reactants, we have the initial rate as indicated by the purple curve is so much faster because there is a much steeper slope. Okay? When using the lower subdivision, as for example when using a zinc granule situation, then the initial rise, the initial steepness of the gradient is less, and less amount of product is produced for the same amount of time when you have a high subdivision compared to a lower subdivision. Okay, so summarizing, if we had to look at this part of your text, if the surface area of a reactant, it has to be at least one reactant, is increased, more particles are exposed to the other reactant, okay? There are more collisions, okay? Instantaneously, there is, in this case, much more of the acid meeting much more of the zinc, and the rate of reaction increases. By the way, this is the reason why you only do these type of reactions with granules, or if you had to do the same reaction with iron, your teacher would not give you iron powder, but rather iron filings. Iron filings, okay, are much coarser, much larger in terms of particle size than would be iron powder. Okay, so a powdered metal would always represent the type of, if you like, subdivision that would result in the highest possible rate of reaction. Okay, it is never safe to give students powdered metal, not just because of the high reaction rate, by the way, but also because of the very high risk of metal inhalation. Whenever I demonstrate any experiment using a powdered metal, I will do so using a fume cupboard and always making sure that the reaction is deep in the fume cupboard, and I would also use myself a mask, and my students are always very far off and at a safe distance away. Okay, that is to say, and use always very, very small amounts of reactants. You use all of the necessary and logical safety precautions that you should. Let's now move on to our next slide. So once again, referring to surface area and subdivision, let's just mention once more that if you are talking about a powdered reactant, okay, there is a faster rate of reaction. We said that there is a steeper gradient at the start, okay, for our reaction curve, and the reaction stops faster because the reactants are consumed faster, and so the curve becomes horizontal sooner. Over here in the picture we have a pictogram showing aluminium powder. Aluminium powder, as the text tells us, okay, it's silvery white, it's metallic, but besides all the health effects, I'd like you to look at the final text that you have over here. It is explosive, it is flammable, and it is water reactive. Now I'm sure that when using aluminium foil in the kitchen, you never thought of it as being explosive or flammable or water reactive. Now all of these added properties are due to the fact that aluminium is a fairly reactive metal. It's quite high up in the reactivity series, but most importantly, due to the state of subdivision. Aluminium is safe to handle in the home as long as it's in continuous aluminium sheets, aluminium foil, because the surface area, you might say it's got a big surface area because a foil opens up into a large surface area. Yes, but if you had to actually really finely split that foil up into a powder, the surface area of the powder would be so much greater than the foil, and that would cause the aluminium to be so much more reactive all at once. Remember, it's a fairly reactive metal, it's got a very high surface area in the powder form, so its chances of reaction are so much higher. It could be explosive in its reaction, okay? In its reactions, it's flammable because, of course, if the temperature had to be a high temperature and you were to be heating the aluminium powder, then it could combust, okay? If you had to heat aluminium foil, it wouldn't react typically, okay? Not at normal Bunsen temperature at least, but I would never risk such a situation with aluminium powder, okay? Because the chance of combustion metallic combustion with the powder is so much greater. Water reactive, yes. Okay, I do remember, okay, once demonstrating to students the effect of surface area on reactivity with water, and aluminium is actually a really good metal to use, because if you had to just put aluminium granules or foil in a test tube with cold water and even heating up the water, nothing will really happen. The reason is that aluminium has a surface layer of oxide, aluminium oxide, that will passivate, that will make the metal relatively unreactive. But if you had to actually repeat, if your teacher had to actually repeat the experiment using a small amount of aluminium powder with a very small amount of water in a boiling tube, okay, and heating it gently in a fume hood, then a vigorous reaction will take place, and the aluminium would actually start to react with the water under those conditions. By the way, do know what an explosion is. We are talking about rates of reaction. An explosion is a very fast reaction, okay, and it normally will release a large volume of gaseous products, okay. There is a particular danger of explosion in factories that handle powdered flammable substances, okay. Flammable means that they can burn in air easily, and even substances that one might regard as being completely harmless, such as custard powder, flour, perhaps even powdered sulfur, because of their finely powdered form, have to be regarded as potentially explosive when stored in industrial warehouses, okay? So temperatures must be controlled, etc., okay? Because the substance could be potentially an explosive because of this much increased surface area. Let's now consider our next slide. So now we shall be looking at the effect of using a catalyst on a reaction rate. A catalyst, by definition, is a substance that will speed up a chemical reaction, but itself does not participate in the reaction, and it is not consumed as a reactant. So if I had to represent a chemical reaction between reactant 1 and reactant 2, okay, to produce a single product, whatever it may be, the catalyst can be included in this reaction only by writing it in over the arrow sign. You cannot write it as a third reactant. You cannot put in cat plus R1 plus R2. That's incorrect. So it is accelerating a reaction, typically. There are also retarder catalysts, if you like, okay, retardants, but let's not talk about them. Let's use the idea to explore those catalysts where the speed is increased, okay, of a reaction, okay, to produce a product or several products. Now, you've already come into contact with this idea of catalysts in year 9, where you would have prepared oxygen in the lab. Your teacher would have shown you that the best catalyst to use for the decomposition of hydrogen peroxide is manganese dioxide or manganese peroxide, the black powder. The catalyst works in a very particular way. Basically, the idea of a catalyst can be very much simplified, okay, by imagining a catalyst to be like a bed, a solid bed, okay, and this solid bed is a meeting point where reactant particles can approach each other and react. So let's imagine that we have these reactant particles, R1 and R2. Now, in the absence of a catalyst, they would depend on a chance collision in space at very high speed. And many times, these chance collisions at very high speed are simply extremely improbable. So, that would translate into a very low measurable reaction rate. However, that reaction rate can be tremendously increased if a catalyst is used. Why? Because the catalyst presents a reacting surface where the reactant particles can land and come close to each other and form chemical bonds so much easier than by a chance collision in space. Once the chemical bond has formed, okay, note that the product removes itself from the catalyst surface, allowing the catalyst to be presented to more and more of the reacting particles. Okay, notice that in this if you like, schema, in this procedure, if you like, the catalyst is unreacted, it is unchanged, and what takes place is the joining up of reactants using what we call an alternative pathway. An alternative pathway involving much less energy, and if much less energy is involved, the reaction rate is so much faster. Industrial processes, many industrial processes such as the Haber process make use of catalysts in order to speed up their chemical reactions and make them economically feasible. Okay, so for example, if we were to talk about the Haber process, which is the production of ammonia from nitrogen and hydrogen, industrial chemists have identified iron as being the best possible catalyst, providing an optimum reaction rate. Okay, if we had to talk about the Ostwald process for the industrial production of nitric acid from ammonia, platinum, which is a very expensive catalyst, has been identified as the catalyst of choice. If we were to talk about the contact process and making sulfuric acid in industry, then vanadium 5 oxide is the best catalyst. So each, if you like, industrial process based on one or more reactions is optimized in terms of reaction rate by a certain type of catalyst. So in other words, I cannot just use iron for any chemical reaction just because it will speed up the reaction between nitrogen and hydrogen in the Haber process does not mean that it is useful for increasing the rate of production of nitric acid in the Ostwald process. Let's now move on to our next slide. This slide will be explored further and repeated when you come to Learning Outcome 15, Metric Assessment Criterion 15.2a. But I think it's a very important slide that I should include in rate of reaction because it really explains why a catalyst is so useful in a chemical reaction and why it speeds up a chemical reaction as it does. Basically, what we already said is that a chemical reaction takes place because reacting chemicals, let's say that we have a reaction taking place between reactant A and reactant B. So let us imagine that reactant A and B will react with each other under normal conditions where there is no catalyst, and they are represented by means of this higher curve in terms of energy. Okay, notice that when the particles are colliding freely in space, they require a lot of energy, okay, in order for a fruitful collision to take place and to produce the product AB. Okay, the AB is the product of the chemical reaction. So a high amount of activation energy is required, and the greater the amount of activation energy is required, the lesser the probability of a reaction. because the chances that reacting particles contain that energy is low, okay? However, a chemical reaction can be much accelerated by a catalyst. I have already explained this to a certain extent in the previous slide when I explained how the catalyst bed provides a surface where the reactant particles can meet and react at lower energy. And that is basically the case. Notice that what a catalyst does is it provides an alternative chemical pathway for the reaction to take place. And the alternative chemical pathway requires a much lower curve, if you like, a much lower energy curve than the uncatalyzed curve. So the activation energy is lowered. It is lowered because the catalyst provides an alternative chemical pathway to the original pathway. The alternative pathway is the pathway where the reactants can meet on the catalyst surface, form the chemical bonds between them, and yield the product at lower energy. Since it is much more probable that many more reactants will have the lower energy required for a catalyzed reaction, therefore the reaction is speeded up. Okay? So basically, the catalyst is promoting the reaction between a big number of low energy particles, all of which would have remained unreacted in the absence of the catalyst. We have spoken about what a catalyst does and how catalysts speed up a chemical reaction. I've also spoken about the decomposition of peroxide using manganese dioxide. The chemical reaction is one that you should be familiar with, okay, and it is shown over here, okay, where you have your hydrogen peroxide decomposing in the presence of manganese dioxide, which we can write on top of the arrow. I would strongly suggest you do so, to give water and oxygen gas. And of course, the rate of production of oxygen depends on the presence or absence of manganese dioxide. Notice, you can use very little catalyst, and if you use very little catalyst, you will still produce oxygen, but as you might expect, you will produce oxygen at a slower rate. Notice that the steepness of the curve, the gradient, is less. Notice when you use a greater amount of catalyst, okay, the steepness of the curve, your gradient is so much greater. So when you use less catalyst, you will produce less oxygen, okay, for a given time than if you had to use more catalyst. If you had to use more catalyst for the same amount of time, you would actually speed up the reaction to a greater extent. Of course, no catalyst, the baseline would remain an unreacted baseline, okay? No catalyst is basically your horizontal axis. There is no observable reaction. So, as you might expect, using more of the catalyst will provide more of a surface area where the reactant, okay, the hydrogen peroxide, can decompose and form water and oxygen. Okay? Let's now move on to our next slide. Over here we shall emphasize this idea that a particular catalyst is linked to a particular chemical reaction. We already linked, for example, iron to the Haber process. We linked vanadium 5 oxide to the contact process, platinum to the Ostwald process, but those are industrial processes. We can actually show that there is an optimum catalyst for a particular reaction even in the school lab. And a very easy way of doing so is by comparing the rate of decomposition of hydrogen peroxide in the presence of either manganese 4 oxide, copper 2 oxide, or zinc oxide. All of these can act as catalysts, but manganese 4 oxide, as you can appreciate from the curve that we have, is the most effective. If I had to take this time T1, okay, represented in this way, I would note that within that time T1, if I used manganese 4 oxide, I would produce the volume as measured on the y-axis of oxygen produced. If I had to use copper 2 oxide, notice that the volume produced, okay, is about a third as much. If I had to consider zinc oxide, it would be a very, very small volume of oxygen somewhere over there produced in the same amount of time. So this clearly indicates that although the three substances can be used as catalysts because they will all speed up to some extent the rate of chemical reaction, there is one catalyst, in this case it's the manganese 4 oxide, which is the optimum one to use. Notice that what the manganese 4 oxide does is it increases the steepness of the gradient. Okay, so the initial rise in the volume of oxygen is so much greater than when compared to the rise either for the copper 2 oxide or for the zinc oxide. The steepness of the curve, the gradient of the curve, can be used as a means of determining how fast the rate of reaction actually is. Okay, it is a measure of the reaction rate. So recapping what we said about the use of catalysts in industry, why are catalysts so important in industry, considering, for example, the Haber process for the production of ammonia gas from nitrogen and hydrogen. Ammonia gas can only be made quickly enough so that it is useful for example, the production of fertilizers, if a catalyst is used to speed up the process. You only stay in the business of ammonia production as long as you can produce the ammonia fast enough. Okay? Apart from the catalyst speeding up the rate of production of ammonia, it also allows the rate of reaction to proceed at a reasonably possible temperature. The temperature of reaction is not too high. Okay? If you used an uncatalyzed reaction, the reaction temperature would have to be greater than that used for the catalyzed reaction. Catalysts therefore reduce the need for high temperatures. They will therefore save on fuel, making it cheaper to produce your desired chemicals, and they will, of course, using less fuel, reduce air pollution. You should know about catalysts as found in living cells. Students who study biology have already come across enzymes, which are biological catalysts, and these are the catalysts that allow all our chemical reaction processes, which are water-based in solution, to take place at body temperature. Without enzymes, all our chemical reactions, all our biochemical reactions would not be able to take place at such a low temperature. Body temperature is a very low temperature, actually. When we're talking about 37 Celsius, we are talking about a very low temperature comparatively, okay? And yet, in spite of the temperature not being a high temperature, these biological catalysts, these enzymes, allow these reactions to produce the products at a fast enough rate to sustain life. So we can also show how catalysts work not just on an industrial scale but also in the school lab itself. The diagram actually represents what can be done in the school lab, but what is typically performed on an industrial scale. It is a way of showing paraffin oil cracking in the school lab. You will speak more about this process when you come to doing the fractional distillation of crude oil. But basically what this experiment involves is taking a small volume of paraffin oil, which is a very oily, okay, hydrocarbon, okay, it consists of basically carbon and hydrogen atoms alone, and breaking it up into smaller molecules, which are more useful in industry and in everyday life, because taking a long chain hydrocarbon and breaking it up into, for example, smaller chain lengths of petrol and other associated smaller molecules will give you a much wider range of commercial uses, okay? But more of that when you come to discussing fractional distillation of crude oil and why cracking is so useful. All I'm interested in here is exploring the use of a catalyst in this particular type of chemical reaction. So notice the setup. The mineral wool that we have at the bottom of the test tube is used to soak up our reactant, which is our paraffin oil. The paraffin oil is vaporized and it is passed over a very hot catalyst. The catalyst is actually broken pieces of pot, okay, porcelain, containing silicate-based materials. The silicate-based materials are the materials that actually catalyze the reaction, and they promote the breaking down of the paraffin vapor into smaller molecule vapors, okay? Those smaller molecule vapors will then pass through the delivery tube and they are collected over here, okay? It could be, for example, a petrol vapor, or it could be an alkene vapor. It depends, okay? It depends on your starting material, okay? Okay, so what this slide emphasizes is that unless you have the presence of a catalyst, such a reaction will not take place. It would be useless to simply heat the liquid paraffin, because just by heating the liquid paraffin in the absence of a catalyst, such a breaking down type of reaction, such a cracking type of reaction would simply not take place. Light is another very important factor that can change the rate of a reaction. And this is one of my favorites to show how important light is when it comes to changing a rate of reaction. Many of you have no experience at all with how pictures, photographs were taken until 15 years ago in Malta, okay, when basically most of the photography was film-based, okay, rather than being digital-based photography. Today, film photography still exists, but it's more of a niche market. We call it film emulsion photography. Without going into too much of the detail, the principle is this, that on the film surface you have a photosensitive chemical. Photosensitive means it is sensitive to light. And typically the sensitive chemical is a silver halide, for example, silver chloride, or more frequently silver bromide, Ag+, Cl-, Ag+, Br-. Now, in the presence of light alone, that silver halide is broken down to give silver. Okay, so the Ag+ is converted into silver deposit, which appears black. Okay, now this reaction of decomposition, if you like, from halide to metal is zero in total darkness, and that's why a film is stored in an opaque to light roll. So the film roll completely excludes light. Okay, so it can be used for a long time, even after being first used in camera. Of course, each film has its expiry date, but even many times it can be used beyond its expiry date. However, once exposed to light, this reaction starts, and the more light it is exposed to, the faster the reaction. The worst offense you can do to taking a film photograph is by having the back of the camera, okay, not well sealed. If it is not well sealed, light will actually find itself and it will fog your film, because the film is only intended for a very little amount of light to strike it. That is all the light that is needed for enough of this decomposition to take place, from the halide to the metal. If you allow entry of light from the back, then this reaction takes place to a much greater extent and you will ruin your photograph. Okay, we say that the film is completely fogged. Okay, so the brighter the light falling on the photographic film or in the darkroom on the photographic paper, the faster the reaction. Okay, and the darker the part of the image that will appear. If we are talking about the image that appears on a film roll, we call it the film negative. And if you put up a film negative to the light, you will see parts of it that are transparent, parts of it that are pure black. Those parts that are pure black are those parts that were most exposed to light. Okay? In the slide, we shall explore the role of light in a very, very important biological chemical reaction. It is photosynthesis. Once again, those students of biology, all right, amongst you will be familiar with this chemical reaction. Typically, it is given as a word equation, but over here I'm representing it in its proper format as a simplified chemical equation, because the equation over here is very, very far off from the actual very complex sequence of chemical reactions that actually take place in photosynthesis. But this is a good general way of representing the overall process. Typically in photosynthesis, okay, as the name implies, photo involving light, so the first part of the name of the word photosynthesis implies the presence of light, and synthesis means to make up. We are making up a sugar product using light. Okay, so that's why we call it photosynthesis. So photosynthesis actually is the building up of glucose, if you like, okay, of a glucose molecule, of a sugar molecule, using carbon dioxide and water in the presence of the proper wavelength of sunlight, or the proper set of wavelengths of sunlight. If the light is missing, the reaction simply does not take place. Okay? In fact, in photosynthesis, there are those reactions that are called the light reactions and those that are called the dark reactions. But even the dark reactions depend on the light reactions taking place in order for them to happen. In the absence of light, nothing happens at all. So clearly, photosynthesis, or the production of plant sugar, is linked to the presence of enough sunlight. And there are experiments that can be used to show that in increased intensities of sunlight, there is also an increased rate of photosynthesis, as can be measured by increased biomass. Biomass represents gain in plant material mass. We are fixing carbon dioxide present in ambient air and converting it into a plant product, sugar, that can then be stored as a complex carbohydrate. Plant carbohydrate is stored in as starch. Okay, so a plant would then gain in mass. Important that you take note of the balancing. Okay, it's a practice also for balancing of chemical equations. On the left hand side of the equation we've got 6 carbons, and we've got 6 carbons on the right. We've got 24 hydrogens on the left, 12 by 2. Over here we've got 12 hydrogens in sugar, so we've got 12 over there, and we've got another 12 in water, 6 by 2, meaning we've got 24 hydrogens. Taking into consideration your oxygens, you've got 6 by 2 oxygens in carbon dioxide, meaning we've got 12 oxygens, and there are another 12 oxygens in water, so it's 24 oxygens in all. If we're to count the oxygens on the right, we've got 6 oxygens in glucose, we've got another 12 in oxygen, so far that's 18, and we've got another 6 oxygens in water, meaning it's 24 oxygens in all. Okay? Now, there is one more slide. It's a video containing slide. It's an excellent roundup of this video presentation because it brings together in one short video the factors that I've spoken about. I've spoken about temperature, particle subdivision, concentration, pressure, catalysts, light. So it explores these factors and how these factors are related to the rate of reaction. So watch the video, watch it by clicking on the play button. As with the previous video, you can pause it any number of times, and that will conclude this presentation on the factors that can affect the rate of a reaction. Thank you for watching and have a fine day.